All right, welcome. We are continuing on with our discussion of single sample t-tests, and this portion of the module will discuss one of the big hurdles that we have with single sample t-tests that we did not have with z-tests, which is that we do not know the population standard deviation for that comparison population, which we generally call population 2. So we don't know that key parameter. We got to figure out how we're going to estimate it. Fortunately, the answer is pretty simple, but it does involve some slightly more complex components of statistics. But when we don't know population means, how did we estimate them? Well, we haven't done it in a hypothesis test yet, not in population 2 at least. But remember, when we want to estimate a population mean, we use a sample mean. That's the best information that we've got. So the answer to estimating the standard deviation is the same. We estimate it, and the best information that we've got is the sample data. So we estimate the sample's variance, then we turn that into a standard deviation, etc., etc. But remember, way back from our variability module, we talked about a problem here with the original variance and standard deviation formulas. Those estimates were biased. They underestimated the population variance. So what we did was we adjusted those formulas very slightly to make them more unbiased. That doesn't mean they're perfect. They still will make mistakes. It just means they're equally likely to overestimate and underestimate the actual parameter. That's what's called evenly distributed errors, where they aren't tilted in one direction. So we've seen these symbols before in Module 4. S squared is a sample variance, but we're using it here as an estimated population variance. Same thing with S. That's a sample standard deviation, but we're using it to estimate the population standard deviation. And here's our old friend, the variance formulas. Again, we have the definitional formula here, the computational formula there. We're going to be using those again. Just like before, it does not matter which one you use, but I do recommend the computational formula, and that's the one I'm going to show you the most of. But if you can get the right answer with the definitional formula, more power to you. Whichever way you arrive at that variance, you then turn it into a standard deviation by taking the square root. So it's just one more step to get the standard deviation. Only difference here is we are using these for estimates of the population parameters rather than just descriptive statistics about our sample. But remember, the adjustment we made to these formulas, as you probably remember, is here in the denominator. The original formulas had n in the denominator. Now we have n minus 1 down there. What that does is it makes the variance a little bigger, which makes it an unbiased estimate. It makes it equally likely to over and underestimate. So here's where we're going to take a little bit of a sidetrack and talk about an important aspect of this process. We're going to talk about it now because it's going to be important for pretty much every hypothesis test we run from here on out. So that n minus 1 in the denominator back there, that figure, just subtracting 1 from the number of scores, represents actually a really important concept in hypothesis testing and generally in inferential stats called degrees of freedom, abbreviated with this little df. The degrees of freedom, I'm going to tell you the definition of it. It's not going to make any sense to you probably. It's great if it does, but it's probably not going to make much sense to you. And then we're going to go over a couple of examples that really helped me make sense of what it meant, what this term refers to. So bear with me. Degrees of freedom as a definition is the number of scores in a data set that are what are called free to vary. What that means is how many scores do we need to fully understand that data set? How many scores would I need to know in this data set to basically be able to figure out every score in this data set? For a t-test, again, it's real simple. It's the simplest formula we're going to see. It's n minus 1. Take the number of people you measured and subtract 1 from it. So very easy mathematically. That is the denominator of our variance formulas, and again, it serves to debias them. So the more people you measure, of course, n gets bigger. Of course, n minus 1 will also get bigger. So the more people you measure, the more your degrees of freedom increase as well. Also, if you know the degrees of freedom, you can just add 1 to it and you know how many people were measured. So it goes both ways. Here are those same formulas. This one might be blocked out a little bit in the bottom right, but it's the same variance formulas, but n minus 1, we're saying that's also called degrees of freedom. It doesn't matter which way you write that, by the way, but that's what's represented by that n minus 1. So what the heck was that definition all about? What does it mean to say that we only need to know n minus 1 of scores to fully understand a data set, and those scores are free to vary? What this basically means is that when we know every score but 1 in a data set, that last score, no matter which one it is, gets locked into place. It no longer can vary. It has to be one specific number. And it doesn't matter which scores we know, it just matters that we know all the scores minus 1. So let's think about this with a real-world example and then with a mathematical example. So here's our non-math example. Let's say you and 3 friends are out eating at a restaurant talking about how awesome statistics is and how you can't wait to try to get a graduate degree in it. And you go out to a restaurant and you sit down and your server comes over, takes your order. The 4 people, you and your 3 friends, you can be whichever one of these folks you want. They order a cheeseburger, a salad, spaghetti, and your most expensive item stuffed with your second most expensive. That's your smart ass friend there. Nobody's really sure what he's doing. He's wasting his money, but I guess it's payday and he wants to eat something weird. So more power to him. So 4 entrees for 4 people. You sit there, the server takes your order, goes away, comes back with the food, and as they oftentimes will, might say, okay, who ordered the burger? And somebody says, oh, that's me, and it goes in front of them. Who ordered the salad? Okay, that's me. That goes in front of the other person. Who had the lobster stuffed with tacos? That's our comedy option. That goes in front of your smart-ass friend who's now regretting it. Here's the thing. 3 of those 4 entrees have been placed. Does the server have to ask who ordered the spaghetti? No. Why not? It's the only person who doesn't have a plate in front of them. It's no longer even a question. Does it matter which 3 entrees she asks about? Nope. Any 3 of the 4 entrees, once she knows where they go, she knows where the 4th one is going. So once any 3 of the entrees are defined, where they belong to is defined, it now locks into place where that 4th one is going. And it doesn't matter which 3. As she's asking those questions about the first 3 entrees, those could go anywhere. There's still uncertainty about where those go. But once she knows where 3 of them are going, there's only one option left for the 4th one. It is locked into place. So to understand the entire data set of entrees, she just needs to know where n minus 1, 3 of the 4 wind up. So her degrees of freedom would be 3. Now let's see what this looks like in a mathematical example. Let's say you have a data set of 5 scores and you know that they add up, that the sigma x is 200. If you know any 4 of the scores, you know exactly what that 5th score has to be. How? Just subtract it from the total. So if someone tells you 4 of the scores are 70, 20, 12, and 30, all we do is subtract them from 200. That 5th score must be 68. It's what's left over. Here's the thing. Until you knew 4 of the 5 scores, those remaining scores could fluctuate quite a bit. There's no way of pinning down exactly what those scores are. So if you know 3 out of 5 scores, the 2 remaining scores, they could vary considerably. There's a lot of different forms that could take. But as soon as you know the 4th one, the remaining score snaps into place. It's whatever's left over from the total. And if you knew a different 4 out of the 5 scores, like we see here, now we know 68. Now, again, the 5th number becomes locked down. It must be 30. So just simply subtracting. Until you know 4 out of 5 scores, you do not know what that last score would be, what the remaining scores are exactly. But once you know any 4 out of 5, the 5th one becomes guaranteed. So we have 4 degrees of freedom here. Either way, even if conceptually, hopefully that makes a little more sense, but even if it's still conceptually a little slippery, it's as easy to calculate as anything. You're just subtracting 1 from the number of people you measure. So degrees of freedom is going to be a part of every hypothesis testing process from here on out. The only reason we don't do it in z-tests is because we know every population parameter of population 2. Here and in every other one, we're going to be estimating some of that stuff. So back to our standard deviation. Again, all that we do is calculate a variance for our sample, convert it into a standard deviation. That's our best estimate for the population standard deviation. But remember, we don't stop there. When we're dealing with sample means, what we want to look at is a standard error to account for that narrowing of the comparison distribution. So because we're looking at a distribution of sample means, we want to change that to a standard error. Fortunately, it's the exact same formula. The only difference is we see S's, where before we saw sigmas. So here's a formula for calculating it when you already have the standard deviation. Or if you just want to stop with the variance, you can jump ahead right to the standard error, divide variance by number of people, square root. That will also give you the standard error. So that's the standard error. It's going to play the same role that it did in our z-tests. It's going to be one of the 3 pieces of information we provide in step 2. It's also going to be the denominator for our test statistic, our t-score that we haven't seen yet. Next up, we are going to talk about some of those pieces of the puzzle, the remaining changes to our hypothesis testing procedure. We're going to talk about how the comparison distribution changes a little bit, and we're going to talk about calculating those t-scores, very similar to z-scores, but it is a different formula.